Hi, welcome to lesson 34. This one is on inverse, joint, and combined variations. Now don't get hung up on the terminology there. We did direct variation in lesson 33 and we want to build upon that. The big one you want to pick up now is inverse, and then you want to be flexible to combining them. So don't get hung up on those other terms. That's just to please the other folks. Now, just like I said before, it's all about the words. And I even put the important words in a pretty color. The intensity of illumination from a light source varies inversely with the square of the distance. Oh. What? Well, now let's think about this. You got a big spotlight on a stage. And we're talking about the intensity of the light, and if you kind of scan down through, something about distance from the light. Okay, so if you're like right here and somebody sticks the spotlight, boom, your eyes are gone, right? Well, if you happen to be 300 yards away from that light, it's no big deal. So the idea is the farther you are from the light, the less intense that light's going to be. That's what that's saying. But here's what's so cool. When you see this varies inversely, after today's lesson, you know exactly what to do. Intensity is going to vary inversely as the distance from the light source. On direct variation, it was a multiplication process. In this case, it happens to be a division. Now, depending on when you're doing this lesson in the whole scope of the course, you might recognize that this is an equation like y equals k over x. And if you saw that particular equation in the past and how we graphed it, part of the graph, just part of it, looks kind of like this. And what's interesting about that is you can see that if your distance, if the x here, the input value, is very small, the illumination is very high. And then as your distance increases, that intensity of the light is going to decrease. But it's not going to be decreasing a whole lot. After a while, it's like, oh, I think I see a light out there, you know? Okay, so that's the basic idea of inverse variation. And here is the format that you should always use in writing an inverse variation. Okay? So yeah, in essence, have the lesson, but let's practice and go on. Now, in this case, we're seeing about this idea varies jointly. Construction costs for a building. Now, in all honesty, I apologize for those of you that are construction majors because I don't think this is how I would do it, but it can be a little bit of an example of a joint variation. The construction costs vary jointly with the number of workers and the cost of the materials. Now, that makes sense. The higher the materials cost you, the more the overall project is going to cost you. The more workers you have to hire, the higher. So this is a direct variation, but with two variables. So now they didn't give me a letter for construction costs. What might you use? I would probably use C. So my construction costs are going to vary. Now I know you didn't see the word directly in there, but you didn't see inversely. So it varies jointly with the number of workers. It also varies with the cost of the materials. Okay? It's in essence like a double direct variation. Okay? So there we go. Your cost is going to be some constant times the number of workers. Obviously that constant is going to include how much you're paying those workers and their benefits, and then the cost of the materials as well. Okay? So that's my variation equation. I don't know what the K value is in this case. I'd have to have some numbers to put in order to compute it. The force of attraction F between two spheres varies directly and inversely, and oh my goodness, what a lot of words. So you take it a little bit at a time. I like this word, varies, variations I'm cool with. I like directly, I like inversely. So now I'm going to start to put the pieces together. What the heck is dependent upon other things? Well, the force varies directly as what? The product of the masses. Well, and they've given me some way to denote these two masses. So, like whatever the mass of this sphere is, I know. I don't know why I put an I. It's kind of a creepy looking guy, isn't it? The mass of that guy, the mass of this guy, okay? And you know where that comes into play? Think about planets. And if you have got some of the really big planets, they have much more pulling power than, say, the formerly known planet of Pluto, okay? That's how the masses are coming into play here. So that would be K times the mass of the first times the mass of the second. But then it goes on and says, and hey, wait a minute, we also have inversely as... Inversely is telling you down in the denominator the distance between their centers. So this distance, and it does say the square of the distance. You just have to read very, very carefully. So that happens to be my variation equation. Now you might want to take a second, pause this, reread it, see where I put everything in there. This is an example of combined variation, but I don't necessarily need for you to know that word. What you need to do is realize that the varies directly, put that up in the numerator, and the varies inversely, put it down in the denominator. Now, some of you may recognize that equation. It's a very, very well-known equation from our good buddy, Sir Isaac. It's the law of universal gravitation. Okay, so, oh, maybe this stuff gets used somewhere in the world. One of my favorite shows, sorry, Big Bang Theory, and I don't know if you saw the episode where Sheldon is going nuts about the cricket. I think he's thinking it's a snowy tree cricket or something like that. You can rewatch that. But we all know that there seems to be a relationship between the number of chirps of a cricket and the ambient temperature, okay? So, as you read through that, we see directly proportional. We love that phrase, okay? So, C, the number of chirps of that cricket, directly proportional to something. Directly proportional tells you you're multiplying it times a constant. Well, let's see here. It is 37 less than the temperature. Okay. So it's F minus 37. Because you'll notice it says the number of chirps is directly proportional to not just the temperature minus 37. So I needed that all in parentheses. Okay? So there is my beginning equation. And then it does tell me, okay, you could sit there for a particular cricket and count, and there were 80 chirps when you knew the temperature was 57. Okay, so I could say 80 for my chirps is equal to K times 57 minus 37. Of course, I picked that because it was a nice number for me to work with. So 80 is equal to K times 20. So my K value is 4. Now, you might want to think about the units on that. That was chirps divided by, that was chirps per minute, divided by temperature, degrees Fahrenheit, okay? So it does tell you that you need to be in Fahrenheit temperature, and it does tell you that you need to have the number of chirps per minute, okay, or that's what you're going to get. So I now know that I have C is equal to 4 times f minus 37. So now, if I want to know how many cricket chirps I should hear, I look at my temperature, or if I want to know what my temperature is, I count my chirps and I put it in here, whichever you want to do. Question is, what if the temp jumps up to 90, or heaven forbid, like yesterday in Springfield, 106? We can put that 90 in right here for my Fahrenheit. Okay, so we would have C is equal to 4 times 90 minus 37. Well, that's what, 4 times 53, I think. And if I did my arithmetic correctly, that'd be 112 chirps per minute with that particular cricket at 90 degrees. I don't know about him, but I slowed down, not speed up. Oh well, it's a cricket. Now another situation that I tried to pull, and I like to pull them from different areas so that, you know, maybe I can hit something with which you're interested. Anthropology, okay? And there is this actual thing called a cephalic index, and it's something that varies proportional to the width and inversely proportional to the length of the head that you find on a skeletal remain. Okay, if they're out on a dig and they pull up a skull, they can measure the width, they can measure the length, and then they can find the cephalic index. And I'll show you in a few minutes, why do we want a cephalic index? Okay. And I have some more information, but we're going to get to that in just a moment. So the first thing I want to do is write the variation equation. Because you know, if you pause me and you read through this whole thing, you get to the end and you're like, what? It can be totally overwhelming. So you slow down, you take one step at a time. That first sentence essentially tells me what my equation is going to be. The cephalic index C is going to vary proportionally or directly with the width. So it's K times the width. That's the direct variation from lesson 33. And inversely as the length. Now you might ask me, so how did we know that? I'm not the one to ask. Go ask the anthropologist. My guess is that they had collected a lot of data and then did a big study and decided that this was the best way to come up with this particular index. But go ask your anthropology profs about that one, okay? I'll help you with the math. So there's my equation. And then I said, okay, in 1921, I think this is all accurate, the Rhodesian man was discovered. I don't know if you've ever heard of him or not. But when they measured, his head was 15 centimeters wide and 21 centimeters long. Okay, so that tells you 15 centimeters wide goes in there, 21 centimeters long goes in here. Okay? And the cephalic index for the Rhodesian man was given as 71.43. So I go in and I say 71.43 is equal to K times 15 and 21. Hey, you know what is slightly interesting here? We're all different on what we find interesting. If I do put the units in here, centimeters and centimeters, in this particular case, those units will cancel out, and this constant will have no particular units assigned to it. Okay? Now, the arithmetic looked like more than I wanted to do there in order to compute that, but you guys know what you'd do. You'd multiply your 21 over to clear your fractions. So I multiply both sides here times 21. And then divide by 15, and we come up with the K value of very close to 100. Okay? By the way, I didn't make this up. That is data that I came about. Okay? So now I can put the 100 in place of my K value, and I have a working equation in order to find my cephalic index. So that if I happen to dig up a new skull, I measure the width, I measure the length, plug it in, and I can get my cephalic index. Okay? Now, continuing on, and I left all this together because sometimes you come upon a problem that's this big, has this much information in it, and it's just overwhelming. And I want you to see that I'm taking it piece by piece. So now I'm down to the question, okay, now that you know the constant, what would the cephalic index be for the Cro-Magnon man? And I apologize if I'm mispronouncing, since anthropology is not my forte. But we've measured, and that guy has a 15 centimeter wide, 20 centimeter long. So I go ahead and plug that in. Here's my width. Here's my length. It was a 20. Now that one, I think I can handle the arithmetic. That should come out to be, what? I think it's 75 even. And I don't know what number of significant digits you might want to carry along. So I wrote the 75.0, but we may or may not want that. Now, that's all well and good. But when I'm doing a problem, I like to know I'm doing it for some reason. Okay? So I went looking. And this is what I found. Again, I'm not an expert, but according to Britannica.com, if you have a cephalic index value below 75, then it's likely that the remains are from an Australian or South African. If you have a cephalic index between 75 and 80, probably European or Chinese, and greater than 80, Mongolian or Andaman Islander. I didn't make it up, but I think that's interesting that then you can go ahead and do your computation, find that cephalic index, and it may tell you something about this particular remain. Okay, moving on to a new one. Please don't think I'm trying to preach to you, but I thought that this was somewhat interesting. If you know much about geometry, it makes total sense that your weight is very much connected to your height, right? Taller people tend to weigh more. The weight varies directly as the cube of their height, and that's because weight is a three-dimensional measurement and height is a one-dimensional measurement. So there's an interesting geometry side to that. So weight varies directly as the cube of the height. Weight varies directly as the cube of the height. See, isn't it easy? Once you start interpreting the words in the problem, variation problems are extremely easy. Okay. Now, I did say, and I think I have it on the next screen. Yeah, let's go ahead and compute our constant. We have got this weight is equal to k times height cubed. And now we know that if we have a person with a height of 63 inches, by the way, that's setting my units then. I'm going to be in standard units, not in metric. This person is deemed, according to the government, to be unhealthy at a weight of 141 pounds. So we're going to put the 141 in for W, 63 in for the height. And now I can compute my K value. Be sure to cube that value first before you divide. And we end up with 5.64 times 10 to the negative 4. Now you'll notice that I did say to find that constant, which we did, and to have it in scientific notation. If you write this all out, what you might have seen on your calculator screen was 0.000564. And that's just a little bit unwieldy to carry around, so we might like it better in the scientific notation. So now I have my K value, and I know, and by the way, this is to be finding that healthy weight limit. But I'm not telling you that I think that is 100% accurate. It's going to depend upon so many things. The makeup of your body and other factors. Yeah, talk to your health people and talk to your doctor. So, weight is 5.64 times 10 to the negative 4 times my height cubed. Okay. If a person's 6 foot 2 inches tall, what is her threshold for the healthy weight? Well, now, what am I going to do with the 6 foot 2? Do I put 6.2 in here? Well, that brings up an interesting discussion because our measurement system here for length is not a base 10 system. I can't use 6.2. And besides, remember that this was all dependent upon inches, and this was pounds. So I need to stay consistent with my units. So 6 foot 2 is what, 74 inches? So I would put a 74 in here for my height, and then run that computation, and we would get a 229, and remember that would be in pounds. So for the 6 foot 2 inch person, 229 is around where a healthy weight limit should be. Okay? Now, how about a recap on this? You know, we went pretty quickly through this because it's not too tough. Because it's all about the words. The words, the words, the words. So use the description of the variation to write that basic equation. You want to look for things like varies proportionally, varies directly, varies inversely. And if you see the words like jointly, varies jointly, that simply means that you have more than one variable going on as input to that equation. Okay? Then you can use some of the given information to plug in to the equation, and as long as you can plug in for every variable except the constant, you can find that constant. Now that you have the constant, you can go out and find other values for that particular problem. Okay? Well, practice, practice, practice. Hope you enjoy it, and don't get scared when there's more than about 5 words in the problem. I'll see you in the next lesson.